Hey guys, Larry C here. Do you know what a caveman's favorite thing to eat for lunch was? A club sandwich. And I hear they like to drink it with club soda. Shout out to you all. Hope you enjoy the video.
Come on now, dog. Come on, man.
But yeah, hey, what's going on, Stat Cats? It's Mr. C here. And I want to apologize if you hear some background noise. My son's playing on his VR right now, and he tends to get a little crazy. So my apologies in advance about that. But welcome to another video where we're going to build a stat course with yours truly, Mr. C. And we are working on section 4.4, which is on counting. And this is based on the Elementary Statistics textbook by Mario Triola, 14th edition. They don't sponsor me or anything like that. I just want to give credit where credit's due, and shout out to the coach gang for and the Money Mindset for reminding me to do all that. And by the way, this is all fair use. Okay, so without further ado, I'd like to start things out just by perusing the section. So normal intro video, key concept here. Then it leads into the multiplication counting rule. Okay, very straightforward. Just multiply the different possibilities together. There's a lot of talk about casino type games, lotteries and things like that in this section, but I did not find anything about probabilities with a standard deck of playing cards unless it's buried in the problems at the end of the section. But that's okay. I have a video that I'll be creating after this one, which will demonstrate the crazy idea I came up with that I'm really excited to unveil. All right, but continuing on, it leads into 5 counting rules. Okay, the first counting rule is the multiplication counting rule. And then it goes into the factorial rule. So here we get to officially define the exclamation point in mathematics. All right, it's not yelling, although it could very well be, but in the context of mathematics, this is typically the factorial symbol, which means take a number and multiply it by all the numbers smaller than it, all the way down to the number 1. Some examples, and then we get into permutations and combinations, and so this is going to be the trickiest part of this section, just so you know. Starts out with a couple of definitions, more talk about cards. I like this mnemonic right here, permutations position, as well as combinations committee. So I'll be mentioning that in my classes. And then the rules pertaining to these. So NPR, okay, not the news station, but this stands for the number of different ways possible when choosing R items from N different items without replacement. We'll talk about barcodes, which is interesting to me because that has some stuff to deal with modular arithmetic. The permutations rule, this is for when we have, let's say, a word with repeating letters. You know, the number of different permutations, order count, when N items are available, so on and so forth. An example, and then the combinations rule. Again, more talk about cards. The formula for NCR. An example to do with lottery. And let's see, this is so this right here is a pretty good example to help differentiate the two between NPR and NCR. Then I believe the next page is the problems for here. Yep. All right, so relatively straightforward section, but you know, the 5 counting techniques that they present will not cover all types of counting problems. There are some that are just extremely complicated, well beyond the scope of this textbook and well beyond the scope of Mr. C's skill sets with this stuff. All right, but what they do include is very teachable and very doable, and I'm sure if you do it right, your students will find success with it. So here's what I came up with for the section notes. I just started out with, I know what you're thinking, wait, don't we already know this? Okay, because, yeah, we've been counting since, you know, as long as we can remember. But the counting here means something a little more intricate, okay? So I put, let's answer that. And I decided to lead off with a formula from an earlier section of this chapter. The desired number of outcomes divided by the total possible number of outcomes. All right, so if a procedure has n different simple events that are equally likely, and if A is an event in the sample space, then P of A equals desired outcomes divided by the total outcomes. So I wanted to lead off with that because of the denominator that we're going to write out. It says here, in many cases, we are not given the total number of simple events. That is, we often have to find n on our own. All right, and then I mentioned that this section will give us 5 strategies, and I put a little asterisk here because, as I mentioned a moment ago, not all counting problems can be solved with these strategies. Some are extremely beyond the scope of our textbook. And even the author states something to that effect in the textbook section itself. Excuse me. So I figured it'd probably be a good idea to define what a counting problem is. Okay, problems in which we have to find the total number of possible outcomes are known as counting problems. Okay, so then I phase into the first of the rules, the multiplication counting rule. And what I did here is I drummed up an example from a previous section or two, just to let the students know that we've already had some exposure to this. Mia is getting dressed for a school picture. She has 3 shirts to choose from, a red one, a blue one, and a green one. She also has 2 pairs of pants to choose from, black and khaki. If Mia picks 1 shirt and or 1 pair of pants, how many different outfits could she put together? So this is a very, very basic multiplication rule. You just multiply 3 times 2, and maybe we'll even sketch out a tree diagram just to illustrate why the answer to this is 6. And that's going to phase us into the official definition for the multiplication counting rule. So I'm going to get rid of that. For a sequence of events in which the first event can occur n1 ways, the second event can occur n2 ways, the third event can occur n3 ways, and so on and so forth, and we're just going to write down n1 times n2 times n3 all the way down to n sub, I don't know, what do we want to do here? Well, they just put an ellipses, so we'll do that as well. So I picked out an example from the textbook that I think is pretty relevant to students of, the usual age for a course like this. Use of ATM cards in hotel safes typically requires a 4-digit, each 0 to 9 code. Digits can be repeated, but they must be entered in the correct order. If someone gains access and enters a code that was randomly selected, what's the probability of getting the correct code on the first try? Express your answer as a reduced fraction if possible. So this is kind of multi-layered. What I plan on doing here is just drawing spaces for each of the 4 digit spaces, and there are 10 possibilities for each of the 4 spaces. So the total number of passcodes, 4-digit passcodes, is going to be 10 to the 4th. All right, which could be kind of a shock factor to students because that's quite a bit of combinations. And if we want to get the correct code on the first try, it's going to be 1 over 10 to the 4th. So pretty small probability, which is why, we even use such a concept for security reasons. And then we get to the factorial rule. So I've seen a few memes dealing with factorial, and so I was looking for some, and I found this, and I really, really like it. Students up there trying to figure out what's 3 times 4, and so he looks back to his classmates for help, and this guy right here is throwing up a very enthusiastic 12. Okay, he's kind of trying to shout it out, but this bloke up here understands that it's 12 factorial and writes out the answer for 12 factorial. That's just classic. So I had to throw that in there. So I first defined the factorial symbol. Okay, denotes the product of decreasing positive whole numbers. And I'm going to illustrate that with 5 factorial. So 5 times 4 times 3 times 2 times 1. And then we get to the factorial rule. The number of different arrangements where order matters of n different items when all n of them are selected is, and that's going to be n factorial. So I altered an example from the textbook to help illustrate this. This is something a band of brothers and myself discuss quite often. How many different ways can the letters of meat be arranged? Okay. shout out to the coach gang. So if the letters of meat are arranged randomly, what is the probability that the letters will be in alphabetical order? All right, so notice that these are 4 different letters. So for the first slot has 4 possibilities. The second slot has 3 possibilities, then 2 possibilities, then 1 possibility. So the answer here is going to be 24 from 4 times 3 times 2 times 1. But there's only one arrangement in which we get the proper spelling of meat here, okay? I might also ask them how many different words can be made by permutating these 4 letters. So maybe instead of using meat, somebody writes out the word team, or maybe mate, or maybe tame. All right, so we'll find those on our own, time permitting. So I figured it'd probably be a good idea to illustrate how to enter in a factorial onto the graphing calculator. So I threw a little bit of technology here. To save time and headaches, factorials can be computed using the graphing utility. So I have some instructions that I just typed out from memory here. And then I thought it'd probably be a good idea to let them know that 0 factorial is equal to 1. And we could even try that out on our graphing calculators to verify it. And I threw this in here, which is kind of coming out of left field, but I wanted to put it in here anyway for the last example of this section. But this is when we have, let's say, maybe we had steams instead of meat. So with steams, S-T-E-A-M-S, there are 2 S's that repeat. So, you know, if we want different combinations, then there's a formula for that, which basically you divide out the repeats. So I'm going to touch on that. And then we phase into the meat of the section here, okay? We get into this right here, does order matter? And so I lead off with some counting methods require that we know the different arrangements of the same items are counted only once or are counted separately. Okay, knowing this leads to the following definitions. So I lead off with definitions of a permutation and a combination. And then I leave a tip for mnemonics. So permutations of items are arrangements in which different sequences of the same items are counted as being different, I believe that is. Counted separately or different, yep. For permutations, they want us to think position, but I might put the word particular in there. And then combinations of items are arrangements in which different sequences of the same items are counted as being the same. So with combinations, order doesn't matter. Okay, so if you switched ABC to CBA with a combination problem, those are treated as the same sequence. So they want us to think combinations committee, but I might think combinations couldn't care less, because you couldn't care less of, you know, whether the order is mixed up or not. So something that I have done in my college algebra classes is I've kind of done like a side-by-side crosswalk here, where I have 2 panels, and in this first panel I'm going to be introducing the permutation rule. And by the way, I made these panels by just inserting a shape, or you could even insert a text box and adjust it to whatever size you want and thickness for the border. But I'm going to go ahead and define the permutation rule here. When n different items are available and r of them are selected without replacement, the number of different permutations where order matters is given by, and then here's where I'll introduce the NPR formula. And as you can see, I have an example down here where we can apply the NPR formula in order to show that, you know, order matters, okay? So this is an image that's generated from Claude. So I just typed in a prompt, can you give me some illustrations that would help me differentiate between the permutation rule versus the combination rule? And after a few trial and errors, I decided to use these examples that Claude gave me. and I just screen clipped them and inserted them into these text box. For the combination rule, when n different items are available, but only r of them are selected without replacement, the number of different combinations, in which case order does not matter, is given by, and then I'm going to give the NCR formula. Okay, so I also have some space underneath here where I'll probably insert some QR codes where I demonstrate how to use both of these rules in the graphing calculator, which I actually recently uploaded a video that demonstrates how to do all that. So I'll probably insert that somewhere down here. Then we get into some examples, okay, and these examples are taken from the textbook. The first example, a presidential candidate plans to begin her campaign by visiting the capitals of 4 out of 50 states. If the 4 capitals are randomly selected without replacement, what is the probability that the route is Sacramento, Juneau, Hartford, and Bismarck in that order? So this is an NPR problem because the order does matter, okay? So the route you take to get from Sacramento to Juneau and so on and so forth is probably different than the route you take to get from Hartford to Sacramento to Juneau to Bismarck. So one thing you want to note here is that your sample size is 50 and that you're selecting 4 capitals randomly from the United States. So that's going to be an NPR problem. The self-driving, so this is the next example, the self-driving unicycle company was recently successfully funded via Kickstarter and must now appoint a president, chief executive officer, chief operating officer, and chief financial officer, and chief human resources officer. I'm going to get rid of that. Seems duplicative. So a CEO, COO, CFO, and a CHR. It must also appoint a strategic planning committee with 5 different members. Now, there are 15 qualified candidates, and officers can also serve on the committee. That's kind of key here, all right? So the first part of the problem asks, how many different ways can 5 officers be appointed? All right, so we want to be careful about that. The officers do have sort of a ranking system here. You know, it is going to matter who is the CEO, who the COO is, and so on and so forth. So order does matter with something like Part A. So this is going to be an NPR calculation. So, so that's going to be 15P5, okay? And for Part B, how many different ways can a committee of 5 be appointed? Now here's where it gets a little tricky, all right? For a committee, it says, let's see, must also appoint a strategic committee with 5 different members. Officers can also serve on the committee. So here you can kind of treat everybody as having the same rank or same seniority. So it really wouldn't matter which 5 people you pick. You just got to pick 5. So because of that, order is not as important. You just need people. Okay, so this is going to be an NCR problem. All right, so that's going to be 15, choose 5. And then Part C, what is the probability of randomly selecting the committee members and getting the 5 youngest of the qualified candidates? Well, there's only going to be one combination in which you have 5 of the youngest candidates. So this is going to be 1 divided by the answer to Part B. So just be careful that you touch on the nuances in those, because that was definitely tricky for me, and I know it's going to be tricky for students. So make sure you don't just blow through these. Maybe draw diagrams out if possible, because the more that they can see this stuff, the better it's going to be for them. Okay, and I decided to throw an extra example in here, and this kind of ties back to the repeated items factorial rule right here on page 2, and then items are selected without replacement and some items are identical. Number of arrangements can be found using this formula where n1 are alike, n2 are alike, and so on and so forth. And I also think it's just kind of interesting. So you become suspicious when a genetics researcher randomly selects numerous groups of 20 newborn babies and seems to consistently get 10 girls and 10 boys. The researcher claims that it is common to get 10 girls and 10 boys in such cases. Use the information to answer the following parts. Okay, so if 20 newborn babies are randomly selected, how many different gender sequences are possible? This is a great shout out to the counting rule, multiplication rule. Okay, so there are two possibilities for each of the newborn babies. So this is going to be 2 to the 20th. So pretty large number there. How many different ways can 10 girls and 10 boys be arranged in a sequence? So this is where you're actually going to use that modified factorial rule, where you have repeated letters. You can think of this as being a string of 10 G's and 10 B's. And so you're going to have 20 factorial divided by 2 factorial times 10 factorial times 10 factorial. Okay, because 10 girls are the same and 10 boys are the same, just in terms of gender. What is the probability of getting 10 girls and 10 boys when 20 babies are born? So you actually want to take, you want to do the 20 factorial divided by 10 factorial times 10 factorial. That's the total number of desired outcomes. The total possible outcomes is given in part A. So you want to take your value from part B and divide it by the value from part A to get your answer to part C. And then I like this one because it kind of gets into some dirty laundry. Okay, based on the preceding results, do you agree with the researcher's explanation that it is common to get 10 girls and 10 boys when 20 babies are randomly selected? Why or why not? This is going to be a great throwback to the 5% threshold. It actually turns out that it is not unusual to get 10 girls and 10 boys, but it's kind of uncommon. Okay, I believe, I actually don't know off the top of my head, I think it's like 17% or something, but I could be wrong. I'll have to double check that. But I know it's greater than 5%, so a great throwback to the 5% threshold. Okay, so I'm going to be back in the next couple of days with something that I created to do a nod to gambling. All right, one of my daughter's favorite things to do, although, she's not old enough, but she buys blind boxes. And there was a video that I made inspired by blind boxes a few weeks ago. But at any rate, I came up with something that would get students some practice with counting card problems. So extra examples with probability and the NCR function. And I'm converting it to a bonus point opportunity. So I'm really excited to present it to you. I'm still working out some of the final details, but I should have that video cut out within the next couple of days. So that's it for this section. Hopefully you found it helpful. If you need any of the resources, let me know. Otherwise, thanks for watching, and hit the like button, subscribe, and all that jazz. Ring the bell for notifications and whatever you guys do. Shout out to you all, Stat Cats. I'll see you in the next video.